Good morning, everyone, and welcome to the May 2025 Sage Live. My name is Giulia Lanza. I'm a material scientist. I work at SLAC National Accelerator Laboratory, and I will be your master of ceremonies today. Today, we're talking about National Laboratories. That is a very exciting topic. But before we start, let me briefly explain what the Sage Journey is and how Sage Live, this webinar, fits in that journey. Sage Journey is a program whose mission is to inspire and encourage students to explore STEM careers for their future. We do this by offering free summer camps, paid internships, professional growth sessions, and other opportunities to connect with professionals who care about you and your future. Sage Live is a part of the Sage Journey. It is an online gathering of students who have attended the summer camp or the internships and are curious about the next step in their Sage Journey. It's also a good time to reconnect with the Sage volunteers that you meet during the camp. We usually held it monthly via Zoom, as you know, between the months of August and May. We cover relevant topics for your journey, either career-related topic about resume workshop, how to prepare for an interview, or exciting topics like quantum computing, AI, and machine learning. So I'm very, very excited to be here today, and I'm going to start my slideshow. If it works. Works? Yes.
Yes.
Okay. This topic is very, very exciting. We are talking about something really unique and powerful in the world of science and innovation, the National Laboratories. I will start with a general introduction. Then we have speakers line up from 7 different national laboratories, and they will share what's going on their lab. First of all, let's dive in. How many of you know how many national labs are present in the United States? Anybody can guess? Everybody can write it in the chat. Question mark. Okay. There are 17 national laboratories in the United States, and they are all supported by the Department of Energy. They are dispersed all around the United States, East Coast, West Coast, as you can see, and in the middle. So probably if you're attending this session, there's a national laboratory close to you. Let's talk about some history. Why do we have national laboratories in our country? So everything started in 1939 when Einstein wrote a letter to President Roosevelt warning him about the potential threat of nuclear weapons. And so that was a very urgent letter. And in this letter that you can see there, he wrote some permanent contact between the administration, the government administration, and a group of physicists working in university and industrial laboratories. So Einstein had these visions to create a collaborative bridge between science and the government to solve something that was really, really pressing, right? A real threat. After that, it came the Manhattan Project. And if you have seen Oppenheimer, you know a little bit about it. And after the Manhattan Project, there was the realization that our country needed a permanent system to conduct long-term mission-driven scientific research. The research that was so broad and so even expensive, or with with the goal that was so far ahead that university and private companies couldn't always do it alone. So the government decided to create these national laboratories. And now today they tackle this kind of big science that require complex instruments, big facilities, and especially multidisciplinary teams that have a lot of skill, different skill, and they get together. And in national laboratories now we are combating climate change, building quantum computer, or securing our energy for the future, because we have all these computers now that need to do AI and machine learning, and we need a lot of energy, right? So why research is important at National Lab? Well, research is not just a game for scientists, just for scientists. It really affects all of us. For example, laboratories help develop the internet, new medical diagnostic and treatment, decode the human DNA, invent new materials, advance in fusion energy. We're still not there, but there's so much that we are doing, and there's so much we have discovered so far. There are new inventions, thousands of new inventions every year, and patents, so we can create new things. And obviously, the national labs, they don't keep everything for themselves. They partner with industry, university. And so research can become real world application. For example, batteries, clean energy system. And so research is taken off the shelf and goes directly into your life through the national laboratories. So here you can see all the 17 national labs divided based on their scope. There are science labs that are primarily focused on scientific research, particle physics, material science, chemistry, biology. Then in the middle section, there are the energy labs that focus on advancing clean energy, grid infrastructure, energy efficiency. And then at the bottom, there are the labs that ensure the safety and security and reliability of the nation nuclear stockpile and contribute to the broader national security challenges. And as I said, we'll hear more about these labs shortly. Where do we find the money to actually run the National Laboratory? Well, most of the labs are funded by the US Department of Energy. So the US Department of Energy gets the money from the government, from the taxes that big corporation, industry, and us pay to the government, okay? So if you think, national laboratory are also your crown jewel, your property, in a sense. So they are funded by the Department of Energy and the government, but they are operated by university or private entity that are running it, they're running the day-to-day activities. So each lab will specify who is running them in the next presentation. They're not only supported by the Department of Energy, some are collaborating or supported by NASA, the National Institute of Health, and the Department of Defense, and they also have, obviously, industry partnership and also international collaboration. So when you say national laboratory, yes, it is a mission that is national, but they really have an impact globally around the world. And I find this link very interesting because you can see all the budget of the national laboratory and the government budget there. So you can check it out. So we received question about why every lab is different. So the reason are both historical and geographical. You can think like superheroes. Every superhero has their own specialty. And so each lab is designed to focus on a specific mission area. For example, Fermilab, it's high energy physics. Lawrence Livermore and Los Alamos specialize in nuclear security. SLAC, where I work, has the most powerful X-ray laser to understand matter at the atomic scale. And it's really historical because, for example, Los Alamos is the national lab that was built after the Manhattan Project, and you can think that maybe they couldn't test the atomic bomb in the Silicon Valley, for example. So there was a lot of land, there was space, and so it started there. There's also another reason. Scientists, really knowledgeable and famous scientists, have their own topic. They really like studying something in particular, and so they push for their topic and their research to be run in a national lab. And it's also very efficient to have all the people, the scientists or the engineer that are knowledgeable about one topic all together in one space, so we can use the government money efficiency and have more results. And this is my introduction. Said that, I'm gonna give it away to Teresa, that she's gonna talk about Brookhaven National Laboratory.
Hi, hello. I apologize if you hear my dogs barking. So she just barked now. All right, yes, I am Teresa Grimaldi. I work at Brookhaven National Lab. I've been there for over 6 years. So I kind of want to talk about the lab a little bit and then what I did at the lab. So you can move on to the next slide. All right, so this is just another map of the National Lab. Brookhaven National Lab is in New York, so it's all the way on the East Coast. I guess it's the easternmost national lab. So I think that's why I'm going first. You can move on to the next slide. So if you kind of zoom in to New York, Brookhaven National Lab is not on the main state of New York. It is not in New York City. It is in Suffolk County, so it's further out east on Long Island. I have a couple of pictures of stereotypical Long Island things. Bagels are very important here. So is the beach. We have some of the best beaches in the world. Lighthouses, New York pizza. I might have to pitch that one over people in Chicago. But we are very close to New York City. So a train ride out to New York City will get you there in like an hour and a half, an hour and 40 minutes. And Long Island has a lot to offer. And a lot of other national labs aren't necessarily in a residential neighborhood. but Brookhaven National Lab is. So it's very funny because sometimes people are taking a hike through the woods and then they stroll on the property and then the police are like, this is a national laboratory. But a lot of people don't even know that it exists on Long Island, just because of how many things there are to do here. So you can move on to the next slide. So what is Brookhaven National Lab? I have our vision, which is to accelerate pathways to scientific discovery and technological innovation that transform the world, which is very generic. So we kind of have four main tenets or like pillars of our mission. The one in the pink is understanding the building blocks of the universe. A lot of experiments that we have are giant machines for studying tiny science. Our relativistic heavy ion collider, or RHIC, it's actually in its final year and doing its final run in 2025, but we smash atoms together and then it makes the quark gluon plasma, and really brilliant physicists and engineers can kind of piece those puzzle pieces together to get the look of primordial matter. The one in orange, developing next generation information science and technologies. That's a lot about what Julie, what you were saying with like patents and all of that research and invention that gets done at the national laboratories can then be offered to the nation. In green, addressing environmental and societal challenges. So Brookhaven has a quantum network that goes between Brookhaven and the local university. That's not something that's ever been done before. They're working on, folks in the biology department are working on biofuels and genetically engineering plants to overproduce oil to then use it for fuel, different kinds of medicines. Brookhaven is a really neat place because it is interdisciplinary. And one of my other slides, I have like a big list, but this last one in blue, leading in discovery with light-enabled science. One of the keystones of Brookhaven National Lab is this right here in my screen background, which is the National Synchrotron Light Source 2. And it's a really popular and powerful user facility where people come from all over the nation, all over the world to use the beamlines there to do crystallography, infrared spectroscopy, and a lot of other really complicated things. You can move on to the next slide. So this is a map of Brookhaven National Lab. We really love circles. We have two very big circles. The one at the top of the screen, it's the furthest north, is the relativistic heavy ion collider, and then the like thicker white circle with the 5 outbuildings at the bottom is the National Synchrotron Light Source. So it's a pretty big place, over 350 buildings and over 5,000 acres of property. We take up the whole town, and that town is called Upton, New York, before it was a national lab. Brookhaven was a World War I and World War II training facility. So walking distance from the Rick Ring, we are one of the few places in the continental or even extracontinental US that has trenches, because in World War I and World War II, the soldiers had to train here and they built trenches to then train the soldiers in. And I actually had the pleasure of meeting a World War II veteran who had trained at Camp Upton before it then turned into a national laboratory. Yes, it is so green. So we're located in the Pine Barrens, which is where Long Island gets its drinking water from. So we're kind of all surrounded by woods and forests of mixed of deciduous and conifers. So it looks pretty and green. Trenches, yes. I have been to the trenches before. You can really only go in the dead of winter because the ticks are really bad. We have a lot of deer and no predators on Long Island. So the deer overpopulate and then there are ticks everywhere. But if you go in the dead of winter and it's super cold, you can actually walk to the trenches. It's really, it's kind of humbling. So you can move on to the next slide. So this is just a bunch of screenshots from Brookhaven's website. So because we're an interdisciplinary lab, you can find those 3 big sciences that they teach in high school: biology, chemistry, physics, and then a lot of other really cool departments. like there's the Center for Functional Nanomaterials, so a lot of material science gets done there. Work on solar panels, things like that. We also have a lot of nuclear groups too. We don't have any reactors. We have an accelerator, medical isotope department. I'll talk about that a little later. And the NNDC, National Nuclear Data Center, that houses all the nuclear data, my accent's coming out, data for the like isotopes, if you look at the chart of the nuclides and stuff like that. You can move on to the next slide. So this is who I am. I started my career in science as a toy soldier at Stony Brook University. I was in the marching band, and I was very happy to put on my uniform for the first time. So I got my undergrad degree between 2016 2019 at Stony Brook. I did an internship at Brookhaven National Lab from 2018 and then a little bit into 2019, and I kind of rolled over right into a job at BNL doing the same thing that I did during my internship with medical isotopes. And then in late 2023, I transitioned over to the Office of Workforce Development and Science Education. And I was the SAGE coordinator for the first ever SAGE BNL camp. And it was really rewarding. So I kind of have seen both sides of the National Laboratory, from the science that is being done and the outreach that is being done, and kind of bridging that gap. So you can move on to my last slide. And I see that I'm at 8 minutes, so I'll try to go fast. What I did with medical isotopes for about 5 years or 6 years, if you count my internship. Medical isotopes are radioactive atoms that are used in treating diseases, or if they're just industrial isotopes, then someone needs to make them. We don't mine for radioactive isotopes. They're made, and especially to the amounts that they need to be made in, you need people producing them. So I listed a couple. Cobalt-60 is a common one. My group didn't make the first three, but these are really popular ones. Cobalt-60, iodine 125 and 131 are really popular for thyroid treatments. Molytech 99 are used, I said, for about 82% of diagnostic procedures. But actinium-225, which is actually the little glowing vial, was being used in clinical studies to treat treatment-resistant late-stage prostate cancer. So that image that I have at the bottom with the guy like this, the first picture, picture A, and actually this is the image that I saw during my internship, and I was like, yes, this is the job that I want to do, because all those little black dots are cancer. And then the guy got 3 treatments of actinium-225, and then you look at image B, and it's like, oh my gosh, it's all gone. And another treatment of C, this particular person is a guy in Germany when they were first doing the clinical studies. His stage 4 metastatic cancer was cured. At the time he went into remission. He lived for 10 more years, and he even wrote a letter, because I think this particular set of actinium originally came from Oak Ridge National Laboratory. Brookhaven was a little late to the jump with actinium. So to make actinium, Los Alamos, Brookhaven, and Oak Ridge all worked together in the tri-lab effort to make actinium. So I had the privilege of being able to go to Oak Ridge. So working at a national lab, we're not just doing our science in a silo and we don't talk to any other of the other national labs. It's a huge network with a lot of really rewarding work and brilliant people. So there, I took 4 more extra minutes. I'm sorry.
Perfect. Thank you, Teresa. Thank you very much. It's very interesting. And the next lab is Oak Ridge National Laboratory, and Alison is going to talk about it.
Thanks, Julia. Okay, thank you. My name's Allison Melton. I am our education outreach specialist at Oak Ridge National Laboratory. I work with our K through 12 programs, internships, camps, all those good things, anything involving our K through 12 students and teachers. So Oak Ridge National Laboratory is located in Oak Ridge, Tennessee. It was established in 1943 as part of the Manhattan Project. We currently have over 7,000 employees, scientists, engineers, technicians, support staff, and our staff members represent over 70 countries. So that's pretty neat. We have a really large campus. We have 32,000 acres. Most of that's undeveloped land. So we have a very natural campus. We have over 1,500 species of plants and animals on our campus that people keep track of. So you always see animals walking around when you're walking to your parking lots and things like that. So that's exciting. And you can go ahead to the next slide, please. Our mission is that we deliver scientific discoveries and technical breakthroughs needed to realize solutions in energy and national security and provide economic benefit to the nation. You can go ahead. So we were established as part of the Manhattan Project in 1943. You can see that picture in the bottom left is the original building that was there. It was called Clinton Lab when it first started. That's the graphite reactor. It is still there, but it's not operational. It's not been operational since the 60s. It's now a historical landmark and museum where people can visit. But that's the graphite reactor. It took them 9 months in 1943 to 1944 to produce plutonium, which was then used in the bombs. But ever since then, we kind of segued away from that to other areas of scientific research. We do exascale computing, fusion and fission, isotope production, national security, solving national security problems, neutron sciences, biology and environmental science, physical sciences, supercomputing, all kinds of stuff. Next slide, please. So here's some recent research highlights that have occurred at ORNL. We're restoring the nation's ability to produce plutonium-238 for deep space missions. That helps power some of those missions that are going to deep space. We're using AI to match cancer patients with clinical trials, collaborating with Google to demonstrate the power of quantum computing. That picture right there is Frontier, which is our current supercomputer. We are about to start construction on our next supercomputer. So we'll see what that one is like whenever it is finished. And then another one is applying human geography data and analytics for humanitarian disaster response and national security missions. So we do all kinds of different stuff. Next slide, please. I've included some resources to learn more. So our website, ornl.gov, is a great resource to check out. We have an interactive map where you can take virtual tours of a lot of our research facilities at map.ornl.org. You can view our educational programs at high school, college, and graduate level at that website. Julia, if I send a link to a video in the chat, can you play it for us? I've got just like a brief video that gives a little overview of what we do.
Give me 1 second, because I need to start sharing something else. Okay. You see it?
We're not superheroes, but we're no strangers to saving the world. From our top secret past to our world-leading present, we use big science to make a big impact. We harness the atom, and now we're figuring out the future of nuclear power and other energy sources for our growing world. We make isotopes to fight cancer, discover new elements, explore Mars, and keep ports safe. We've been building the fastest computers in the world for years. And now we're using AI to accelerate our discoveries. Scientists from all over the world come to Oak Ridge because of our unique research facilities. We make manufacturing smarter, bigger, more efficient, using all kinds of materials. We even create new materials from the atoms up. Companies love us because we help them solve problems. Startups love the expertise that helps them get off the ground. Want breakthroughs that give us the best batteries, fuels, and vehicles in the world? We're working on all of that. How about control of nuclear materials, a safe power grid, computers that can't be hacked? We're working on those too. We study our changing world for insights into the future. And we're still seeking new knowledge, discoveries that can change the future in ways we can't even imagine, diving into the quantum realm and building models of the stars. We bring together some of the best minds in the world to solve some of its biggest challenges. We inspire the next generation, and we're ready for whatever the nation needs next.
Great, thank you. So that is a rough overview of ORNL. Yeah, we can move on to our next lab. Thank you all.
Thank you, Alison, for the presentation. The next national lab we're going to talk about is Fermilab, and Cindy is going to talk about it. Hi, Cindy.
Hi, Julia. Hi, Daniela. Just a second. I'm sorry. I realized one of my slides is a little messed up. So if you give me like 10 seconds, I'm sorry about that. Sorry, did you guys hear me? I'm sorry. Can you?
Yes,
Did you
yes.
need
Can
me
hear
to
you.
speak
We
or
can hear
not
you.
hear me?
Yes.
Okay.
Yes.
Yes.
Sorry.
Sorry about that. Just a moment.
In the meantime, can you guess in the chat where is Fermilab? Let's see. Somebody's gonna guess. Is it written already? Oh, it's not written in the slide, so.
Make a guess.
Not in New Mexico. Right, Anna. There's a hint somewhere in the Midwest. Anybody wants to guess? No, it's not in California.
Pizza rivals.
Illinois, yes.
Yeah.
Good job, Natalie.
Yeah.
Okay, thank you, everyone. I'm hoping that this will work as it is. Thank you so much for the layer. So I'll go ahead and get started. Hi, everyone. Thanks for coming on a Saturday afternoon and everything. Really appreciate having you here. So happy to see all your happy faces. So my name is Cindy Joe. I am an engineering physicist at Fermilab, which will tell you where that is, or more about where that is. And happy to represent our beautiful lab. Next slide, please. So we are, as all these other labs are, we're one of the 17 Department of Energy national labs, and we're the only one that has a single focus specifically on high energy particle physics and accelerators. So we're also known as America's Particle Physics and Accelerator Laboratory. We're called Fermilab as a sort of shortened form of a longer form of our name, which is Fermi National Accelerator Laboratory. We feel like the accelerator part is really important. It's named after Enrico Fermi, the famous Italian physicist. It was originally called the National Accelerator Laboratory, and later on they put Fermi's name onto it in honor of him. So we started operations in 1967. That was about so we've had our 50th anniversary already a few years ago, and we're located in the suburbs of Chicago, Illinois. There we are in the Midwest, right next to Lake Michigan. So we're about 30 miles west of Chicago in a town called Batavia. Our site is about 6,800 acres. So I realize in talking to the other labs, some of the labs may think that's really big and some of the labs may think that's really small. So it's about 10 square miles. And in addition to physics research related uses, if you can go to the next slide, much of the site is carefully restored tallgrass prairie, wetland, forest, savanna. If you can back up a slide a little bit. We have ecological programs, and we even have a lab ecologist. So this slide that I'm showing you, that's sort of our main office building that's called Wilson Hall in honor of our founding director, Robert Wilson. And it's just this like beautiful cathedral shaped thing that was, he was inspired, the founding director was inspired by cathedrals in France and wanted this beautiful vaulting sort of atrium structure. So we think it's really beautiful and unique, and we're really proud of it. Next slide, please. So on the top left is a aerial view of some of our accelerators. The one sort of larger ring on the right that's more of a circle shape is was originally the main ring accelerator, now also was then later the Tevatron accelerator, which was the highest powered accelerator in the world for over 25 years. The sort of more oval shaped one in the foreground is our main injector, and it's our real workhorse right now. And you can see like kind of like the little bitty outline of Wilson Hall sort of in the middle near the top. So our founding director, one kind of weird fact about Fermilab is we have a herd of about 35 American bison. Our founding director wanted to represent like frontier science. So somehow he got a herd of bison, like the Department of the Interior, I think, just gave them to him. And so we have taken care of them ever since. So we have at least a dozen adorable new babies born so far this spring. They have like 20 or so babies every spring, and we've already started having our babies. They're super, super cute. If you ever get a chance to come out and visit them, we would love you to. They're kind of like a little bit of an unofficial mascot. And that image on the bottom is just a picture of the, oh, sorry. Let's go on to that might be a messed up one. Can we, one of the pictures is going to have the correct image. There we go. If we can play that video, I'm sorry, I think that one got a little bit messed up. Thank you, Julia.
At Fermilab, we study nature at its most fundamental, drilling down to the smallest scales of matter using some of the largest and most advanced machines in the world. Accelerators, powerful microscopes, send particles barreling at near light speed into other matter, creating subatomic scraps. Detectors zoom in on those fleeting pieces, making the invisible perceptible. And sophisticated computers sweep through all of it, crushing mountains of information into gems of data. We also use our cutting-edge technology to explore the mysteries of dark matter and the quantum realm. Thousands of scientists from around the world partner with Fermilab to explore how the universe works, expanding humanity's understanding of matter, energy, space, and time. Fermilab is solving the mysteries of the universe.
Sorry about that. That was just a little intro video to kind of give you a sense, a little taste of what we do at the lab. Again, the mysteries of matter, energy, space, and time. We're trying to do this sort of fundamental physics research, and it's the sort of research that there's not always an immediate return on investment for. There's not always like an immediate technological development that comes right out. But the discoveries that we make, this fundamental work, allows us to spin off into all sorts of incredible research that does hit the market, that does allow us to make medical discoveries, to make computing discoveries, to make all sorts of interesting things happen. So again, as the video mentioned, accelerators are one of our primary tools of high energy physics. They're kind of like microscopes or telescopes. They allow you to observe things that are otherwise invisible to your perception, sort of control how that works. So depending on the area of study, we might want to reach very high energies, which allows us to probe incredibly small things like the interior of the atom. Or we might want to reach very high intensities to have lots and lots of particles, which allows us to probe things that occur very, very rarely. So those allow us to focus in different ways. But historically, the focus of the lab was higher and higher energies. Higher and higher energies allows us to look at smaller and smaller things. So we use the main ring accelerator and then the Tevatron, which I mentioned earlier, which is a proton-antiproton synchrotron collider, a lot like the Large Hadron Collider in Europe, if those of you have heard of it, but which came later. But they are a proton synchrotron. We are a proton antiproton. We sort of focus on slightly different things. We made a lot of great discoveries in addition to being a part of the Higgs boson discovery that was there in 2012. We made a lot of discoveries in our own right. So the top quark, the bottom quark, and tau neutrino, which were our fundamental parts of the standard model on the right, were all discovered at Fermilab. There's some pictures on the bottom of some of the detectors responsible. Next slide, please. These days, the lab really focuses, one of our main focuses in the lab is our neutrino program. So we're the host lab for a program called LBNF Dune. That's a long baseline neutrino facility, or the Deep Underground Neutrino Experiment, which is the largest and most ambitious project and experiment of its kind. So we're shooting the most intense beam of neutrinos ever made at the largest neutrino detector ever made at the deepest site for this in the Black Hills of South Dakota. So we're really excited about that. And we're developing a next generation accelerator that will feed that accelerator complex as well. I know that I'm going a little bit over on time, so I'm going to try to speed it up a little bit. But we also do work with muons. Muon G-2 experiment is searching for physics beyond the standard model. Mu to E is this experiment that's just getting ready to get started. It's a muon to electron conversion. Hopefully we'll be able to observe that maybe. And we also do cosmic research, stuff about dark matter, dark energy, technology research, accelerator development, and so much more. Some of those pictures on the right, sorry about that. Some of those pictures on the right include a diagram of us sending beam to the Deep Underground Neutrino Experiment, the ring for the muon G-2, and then some telescopes in Chile where we have the Dark Energy Survey and several other telescopes. Next slide, please. And just a little bit about me so that you know the face behind the physics. I grew up in Arkansas and a first-generation college student. Maybe that's something that some of you can relate to as well. I have a bachelor's in physics from Reed College. It's in Portland, Oregon. While there, I got to work on Reed's nuclear research reactor. That's the top right picture. That is me above a working nuclear reactor. It looks exactly like that. It's amazing. I've been at Fermilab since 2010, and I started out as an accelerator operator. I love big science machines. That's how that went. And I'm currently an engineering physicist, which I summarize as I'm somebody who solves problems. Again, I work primarily with neutrino experiments, and I'm in charge of a few different facilities there. And some of the things that I really love include educational outreach, science advocacy. There's a picture of me along with a group in DC. And running. I completed 3 full marathons, and that's a lot of fun for me. So thank you so much for listening.
Thank you, Cindy. Thank you for your nice presentation about Fermilab. And now we're going to switch to Los Alamos National Lab. Anna is going to talk about it.
Hello, everyone. They have been showing off all their greenery, and here I'm talking from New Mexico. We are in the middle of the desert, so let me take you for a ride. Next. So where are we? We are, if you look on the screen, I pointed where we are. We are in New Mexico. We are about 7,300 feet high above the sea level. Can you click one more time? And we are pretty huge compared to other national labs. We are the size of Washington, D.C. in terms of square footage. Basically, this laboratory was the origin of the county. There was nothing else here before we came. Next. So who am I? I'm a physicist. Material science was experimental material science was my background. I went into shock physics, and now I'm working in national security projects in a place called X Theoretical Division, and working on safety and surety. And what I wanted to show here is I come from far away. I was born and raised in Barcelona. I went to college in Barcelona. I did my PhD in Grenoble, France. If you go, keep clicking, Julia, pictures will show up. I did my PhD in Grenoble, France, and then I went above the ocean and I landed here in Los Alamos. As I jokingly said, it's almost lost because it was really in the middle of nowhere. So, so you see, we have scientists in the national laboratories from all over the world working on pressing scientific issues. Next, you might need to keep going. So my sage word is resilience. I wanted to share that with you guys because Dory and Nemo are my heroes. And when, you know, the image of when life gets you down, what do? You just keep swimming. Guess what? That's resilience. The goal I can control is to aspire to be relevant. Sometimes we give ourselves goals that don't depend on us. Like my goal can be to be a president of the United States, but it doesn't depend on me, right? So my goal is to be relevant, and my personal aspiration is to be the change I wish to see in the world. And I put all these things in the work I do day in and day out. Next. And you're gonna say, yeah, that sounds very, positive. So when life gives you lemons, I'm strongly encourage you all to call Joy. Joy is always on call, and to find your tribe and love them and let them help you, and then to learn to sell your lemonade because ups and downs will come, but if you're resilient, you're gonna get over it. Next. So Julia talked about national labs, and if you can click, that would be fantastic. What I wanted to show here is that we solve problems of scale, problems that require a lot of people, a lot of disciplines, sometimes with equipment that takes decades to build. And you already heard some of those equipment, like large accelerators, neutron reactors, and things like that. These are not things that universities themselves or industry alone can do. So national labs are here in this country to solve things that we would not be able to solve otherwise. If you continue clicking, Julia, there's I think one more, and we can go to the next slide. And one thing that Julia mentioned is that there are national labs that work in specific topics, and some national labs like Livermore, Sandia, and Los Alamos, we are part of the National Nuclear Security Administration, and this is the entity that maintains a safe, secure, reliable stockpile. Stockpile is our weapons, right? And prevent the nuclear terror. And what we do, sometimes you just think, oh, things that go boom. No, we can be threatened as well with energy security issues, infrastructure. Someone cuts down, prevents our electricity to flow in the country. That's also a threat, and it would be terrifying, isn't it? We also work on health security. Well, we just came out of a pandemic. We couldn't have thought about it before. And we also work very closely with industry in what's called economic competitiveness, making sure the United States is at the forefront. We'll take people from all over the world to ensure the country is at the forefront of discovery. Next. So I just ChatGPT when was Lionel designated National Laboratory, and here's what it told me. And although the National Laboratories, as Julia mentioned, started as a multi organizational effort to solve something very complex. You have heard today that several national labs like Sandia, Oak Ridge, and others, we all started about the same time because of that reason. Next. So we have been 82 years serving the nation. The mission of the laboratory is to solve national security challenges through simultaneous excellence. And you're gonna ask, whoa, what excellence? Well, we not only care what we do, how we do it, and how our impact on our surroundings. So our vision is to be trusted by our nation. That means a lot. emulated, so copied by our peers and respected around the world. If you are in school, you might not want to compete in math with someone who's very good at math. So we are doing the same in this country when it comes to science. We rely on all those scientists, engineers, and technicians and technologists to ensure nobody, dare to challenge this country and keeping our national security tight. And as it says here, our culture is also very important. It's not only how we do it, but what we do, but how we do it. So sometimes we need to take some risks to get stuff done, and sometimes, but we focus a lot on all this communal knowledge. Our values are the service, integrity, teamwork, and excellence. And that sounds like keywords, but when there is a threat to the United States, we drop what we are doing to be able to address that threat. That means that us who work here, we need to be able to be very agile and switch from one topic to another. And you saw that in my career, material science, you saw shock physics, and now you see national security. Next, don't worry about that. We will go to the next. We make sure that the threat, we don't have a spread of nuclear weapons in the world as well. Next. Fantastic. So as I mentioned, we have a huge budget, lots of money, 5.1 billion in budget, about 40 square miles. More than 13,000 people work here at Los Alamos National Laboratory, and we get around 1,600 students a year and 550 postdocs. And the average age of the employees is about 47. You know what that means? We need you all to go and get your degrees and come over here. And we are working very hard on diversity, and 35% of our employees are women. And we also make sure we have this diversity in the workforce, because with diversity is when we get the best of the best. Next. So I asked ChatGPT what are the 10 greatest achievements of Los Alamos National Laboratory, and you heard of several: the atomic bomb, the hydrogen bomb. We also delivered the Roadrunner, a huge computer. And you were going to say, why do you need such a huge computer, so much money? Well, national security, climate change, biomedical research relies on high computing, because we cannot test everything experimentally. We also have a very strong plutonium science and non-proliferation. Non-proliferation means that we make sure the other countries are behaving per the agreements that they signed with us. Oh, no, we are not going to develop nuclear weapons. Guess what? Like with your friends at school, trust your friends, but verify that they are not lying. We are also working on genome research. So making sure we can track all those DNA strands on things that are going around the world, and material science and national security, as well as biosecurity. And we took an important role during the COVID-19 pandemic. Our engineers and scientists, again, we dropped what we were doing to figure out how we could impact addressing the pandemic in this country. Next. It's okay. Explosive space research. You have half a mile long, 800 mega electron volt proton accelerator center for integrating nanotechnologies, 100 Tesla magnets. We try to have it all in the middle of nowhere. Next. I mentioned that, so I'm gonna, an important thing here is 40% of our technical staff are hired, are former postdocs or students. I came to Los Alamos as a postdoc. I got hired after my postdoc was over as a staff member. So doing those internships is very important, and the earlier you start, the best, as you heard several speakers. Next. And that's it. Consider career. I'm going to encourage you all to consider career in Los Alamos National Laboratory. If you want to make a difference, if you enjoy working with others, because guess what? Your neighbors are going to be your colleagues too. It's such a small place. And you want to be part of something extraordinary. Here you have some pictures of our landscape. It looks green, but we are very high up. It gets cold. The growing season is very short, so it's a nightmare. And we have bears and coyotes, and we don't have an overpopulation of deer. So I'm going to leave with that. It's an amazing outdoors community. It's very safe, and it's filled with nerdy and artsy people in town that make this place fantastic. Thank you.
Thank you, Anna. Thank you for talking about Los Alamos and bringing your energy to the group. It's always a pleasure. Thank you. And now Joanna and Gianpaolo, I guess, are gonna talk about Livermore National Laboratory.
Well, hi, everybody. I'm Joanna Albella, and I'm the Science Education Program Manager at the lab. And I'm going to start off this talk, and then I'm going to give it over to my partner in our SAGE efforts, GP. Can I have the next slide, please? So a little bit about me. I started at Livermore over 30 years ago, like Anna, as a postdoc, which is sort of like after you get your PhD, similar to a doctor, you're not quite ready to be independent. So a postdoc is another learning opportunity before you become an independent scientist. I started my educational journey at Bucknell University, and our mascot was a bison. So Bucky the Bison came to all our football games. So I have seen a big bison, not at a zoo, but alas, behind a cage. My journey after getting my undergraduate degree was to get into the workforce because unlike classes at universities today, there was much more limited number of options, and I wanted to see if I really wanted to go on and get a PhD. So I wanted to know if I would enjoy the work out in the field, and I did. And then went on to get my PhD in biology at Albert Einstein College of Medicine, and then I came to the lab. So I did my postdoc and ran a research group at the lab when Livermore was part of the Human Genome Project, as Anna mentioned. It was a huge effort at the National Lab System and in partnership with companies and the global scientific community to sequence the human genome. So I was very proud to be part of that effort. And then my journey took me into a more academic area. I left the lab, went to UC Davis and was a professor there, then to the University of the Pacific, which is a local private institution in the Greater Bay Area, and was a professor there. And then did a little work at community college and came back to the lab several years ago as a science education manager. And it's been an absolute joy to come back, knowing how the lab works and having been a scientist here. And that gives me a great foundation to then share our science with young people as the K-12 manager. Next slide. We also have a lot of geese. I would say that is our primary mascot. We are covered in geese. So Livermore was established in 1952. We were grown out also sort of out of the Manhattan Project. If you do see Oppenheimer, Livermore, and Ernest Lawrence and Edward Teller were part of those efforts. And after the Manhattan Project was wrapped up, they wanted another laboratory to do similar national security work. So we were born. This is an aerial view of our 1 mile square facility that hosts more than 9,500 employees. We are sister labs. We do a lot of partnership work, as Anna's just put in the chat. We have over 500 facilities and an annual budget of over $3 billion. We're operated by Lawrence Livermore National Security, which is a conglomerate of a number of different institutions and companies, including the University of California system, which was our parent operating system for many, many, many years. So Livermore was a formal naval base, similar to what we heard about Brookhaven Lab. And so it was a great site for Teller and Lawrence to go to Congress and petition to have our laboratory. And so again, we have been in operation now for over 70 years, approaching 75 years. And we have an operational test site back behind us in the hills of Tracy, heading more eastward out toward the Sierras, which you can see sort of under the clouds. It's a very green view in this picture, but we get a little toasty in the summer when the weather gets super warm. Next slide. So this is just a picture to give a little bit more depth about the physical site. So in that green area in the middle-ish of the slide here, that's our open Livermore Valley Open Campus. And the Livermore Valley Open Campus is where a lot of our educational programs work. It's also where we have the University of California Collaboration Center, which has been part of the lab's outside the fence system to allow for a lot of collaboration for over 60 years. And we sit right next to Sandia, California, which is that little eagle emblem on the right-hand bottom side. And the reason that the lab wanted to have these facilities was to have more access for capabilities and collaboration with outside entities. Next slide. So we have a very talented and multidisciplinary technical workforce to accomplish our mission for enabling U.S. and global security and resiliency, to empower multidisciplinary teams to do great innovative science and technology. So I like to show this slide to say that you don't have to have a PhD to work here. There are people with terminal degrees of all different natures, and your terminal degree should match the job that you are coming to the lab to do. So yes, there's a lot of PhDs and people who've done a lot of schooling, but there's also a lot of people who don't have a PhD as a terminal degree. Next slide. And so LLL invests locally in educating the workforce of tomorrow by being involved with programs like SAGE, and in doing all sorts of different types of work. I want to make sure to say that before I introduce GP to talk about more of the science and technology we do, that we do every kind of STEM that you can imagine at the laboratory. But we also need lawyers, and we need accountants, and we need business people, and we need administrative staff. So really, there's a place for everyone at the lab. We do function like a small university or campus, and I'm just very fortunate to lead the team that gets to do all this fun stuff, bringing students to the lab. And with that, I'll let GP take it away.
Great, thanks so much, Joanna. So I'm GP, Gianpaolo Carosi. I'm a particle physicist here at Lawrence Livermore. One of the things I really like about being at the lab here is that you can work on very fundamental science, like what's going on at Fermilab. We have lots of partners that I work with at Fermilab. I primarily look for dark matter as part of my day job. I also work on some national security projects. You use the same technologies there to try to look for hidden nuclear material, people trying to smuggle in nuclear material, and look for these rare signatures. I grew up north of Seattle on Whidbey Island and went to school both for undergrad at Harvey Mudd in Southern California, and then did my PhD over at MIT, where I got to work on a space experiment called AMS, which is still up on the space station, which was a lot of fun. My sage word is curious, and that's one of the reasons I love being here at the lab is I've never been bored here. There are so many things going on, and it's really just, you know, the journey you can take here, have multiple jobs, have different jobs at the same time if you'd like. Next slide. So focusing on Livermore, as we've kind of talked about, a lot of the labs are multidisciplinary, and Livermore is also one of these multidisciplinary labs. We have a lot of what we call core competencies. These are things that the lab itself has invested heavily in over the years and is very good at. One is high energy density science, and for that, think of like the National Ignition Facility, which I'll talk about in a minute, where you make very dense objects. Biosecurity, bioscience. We have a BSL-2 lab. We were very heavily involved during COVID on coming up with solutions to that. Earth and atmospheric science, advanced materials manufacturing. We have very cool 3D printers, very unique in the world 3D printers. Lasers and optical science, nuclear, chemical, and isotopes. And of course, high performance computing, simulation, and data science. Next slide. So all of those kind of competencies rely on facilities, big facilities. National Ignition Facility, which has recently gotten ignition, which we've actually seen fusion, controlled fusion here on Earth for the first time, not just in bombs. Livermore Computing Facilities, Site 300, which was mentioned earlier, that's that off-site location. And a little fun fact, Livermore is known as Site 200. Lawrence Berkeley, which will come up next, is Site 100. Site 300 is out in the hills, and they do explosives work out there. We have a polymer science, a lot of material science, advanced manufacturing, and a lot of high explosives testing. Next slide. So really a lot of these facilities here work together. And the way we like to think of it is there's a multidisciplinary process where you'll come up with computing, you'll come up with your ideas that you want to test. We have 14 systems that are in the top 500 supercomputers, and I'll talk about the fastest supercomputer in the world right now, El Capitan, in a second. We then want to be able to take whatever we've modeled in these computers and actually do experiments on them. And so an example of that is like the National Condition Facility, where all this modeling was done, and we wanted to actually show that we could make kind of these little artificial stars here on Earth. And finally, accelerated materials and manufacturing kind of completes that loop where we actually can start building some of these materials that we've modeled and we've experimented on. We can manufacture them, we can actually work with companies and try to get them out into the economy. Next slide. So I'm going to talk about two things real quick that we're really proud of recently. One is supercomputing. So El Capitan is the world's fastest computer, and it will be for a little while. It's always a friendly competition if you ever go to the top 500 list. It runs right now at approximately just under 3 exaflops per second. And this is a crazy number to think of. So an exaflop is 10 to the 18 flops. And what's a flop? Flop's a calculation. And to give you an idea of the scale of this, if every person in the world did one calculation every second, it would take them 8 years to do what El Capitan can do in 1 second. So this is just an incredible computing facility. Next slide. The other thing that we've been extremely proud of recently is achieving fusion ignition for the first time. So the diagrams of what I have right here show in red how much energy in our laser system, and it's an amazing system. It takes 192 laser beams, focuses on a tiny little peppercorn-sized pellet of hydrogen, tritium, different mixtures of hydrogen and helium, and creates a little tiny explosion. And to give you a sense of scale, the red is how much is going in, and then the larger circle is how much energy comes out. So we're actually making fusion and the energy out. So we had, for the very first ignition back in December, 2 megajoules going in and 3.15 megajoules coming out. And since then, we've been able to scale upward. And to give you a sense of scale, a megajoule you can consider as a stick of dynamite. So this is all light power going in, an actual tiny little fusion reactor being created for a fraction of a second. So these are just some of the things that Livermore does, and we have a huge student population. We'd love to see somebody here this summer or as interns in the future. So with that, I'll hand it over to Berkeley.
Thank you, GP and Joanna. That was great. And I love this actually explanation about the fusion and how it worked. It's very nice. And now we are giving it back to Faith to talk about Berkeley National Laboratory.
All right. Good afternoon, everybody. I'm Faith Dukes. I'm Director of our STEM Education Programs here at Berkeley Lab, covering our pre-college, college, and faculty programs. I'll say a little bit about me before I get back into Berkeley. I have my PhD in physical chemistry. I studied wastewater remediation, so how to clean waste and water with light. As a graduate student, and I'm originally from the East Coast. It's been a great journey to think about being a scientist and being in a scientific laboratory, getting an opportunity to then transition to outreach and education. So I've had positions at MIT in their museum as an education coordinator, and then doing policy work in STEM education at the National Science Foundation before getting to Berkeley Lab. So on our next slide, you're going to see the 17 labs that you've seen. We are one of the 4 national laboratories in California, Lawrence Berkeley National Laboratory. So another Lawrence. And on the next slide, you'll see EO Lawrence, Ernest Orlando Lawrence, and our current director, Mike Witherell, who manages the laboratory. One of the quotes from Luis Alvarez that I like to put up is that Lawrence will always be remembered as the inventor of the cyclotron, but more importantly, he should be remembered as the inventor of the modern way of doing science. And that modern way of doing science is with team science. So people coming together to solve really big problems together, as you've heard of throughout this session. E.O. Lawrence started invented the cyclotron, so particle accelerator science early on in the 1920s, 1930s as a professor at UC Berkeley. So Lawrence Berkeley National Laboratory is just above UC Berkeley in terms of our geography. You can see our advanced light source, which our cyclotron went into a synchrotron after many years of doing wonderful and innovative research. And E.O. Lawrence brought a number of people together. We are celebrating, we were founded in 1931 and we'll be celebrating our 100th anniversary in about 6 years. So we've one of the first national labs that was founded, and you can see a number of accolades or by the numbers with 16 Nobel laureates, 16,000 researchers using facilities worldwide, 4,000 employees almost, and a number of scientists, engineers, researchers, and postdoctoral researchers. So on the next slide, you can see a picture of E.O. Lawrence at the bottom. And you'll see at the very top, sticking his head out, is Oppenheimer that we've been discussing so much. So this is actually at Berkeley Lab on our magnet yoke within the advanced light source. We can't take that picture now, mostly because our environmental health and safety group will not allow us to climb up on the magnet yoke, but we've tried to recreate this picture in a number of ways. So as everyone has said, we are solving big scientific challenges. We are funded by the US government, by the Department of Energy, and we are managed by the University of California. As a part of the work that we do, we also have an extensive STEM education and outreach program. So on the next slide, you can see some of our students from last summer. These were students in multiple high school programs with our director during our ice cream social that we held. And we are dedicated to making sure that more and more young people get an opportunity to not only learn about scientific research at the national labs and at Berkeley Lab in particular, but also to understand how they can be a part of that ecosystem and a part of the National Lab complex. So I'll point out our scientific focus areas on the next slide. So just wanted to highlight, as many people have said, a couple of people are focused in on specific scientific areas, but we are an interdisciplinary laboratory. So biosciences, including being a part of the human genome, not human, but the genome project, and having our integrative genomics building and our joint genome institute in biosciences. We're part of a dark energy spectroscopic experiment in our physical sciences. We also have a supercomputer in our computing sciences, and this is Perlmutter, named after one of our Nobel laureates, Saul Perlmutter. Energy sciences has our advanced life source. Earth and environmental sciences are thinking of multiple ways and enriched to think about how our world is changing and what we can do to support it. And our energy technologies area is thinking about how we do everything from heat and cool our buildings to new technologies that will support our electrical grid. So these are all the things that our scientists are doing at Berkeley Lab. I say we just don't go to the hospital or to the moon, but we do everything in between. And so it's wonderful to work with so many scientists who are great at sharing their research and at doing things that are so innovative that are changing our everyday life. And finally, you can see one of the long-standing research efforts that we've had. So Berkeley Lab was originally named the Rad Lab. So on the next slide, you can see the 16 elements that we have been a part of founding or discovering. We are still on the discovery pathway. So this is a picture of one of our researchers, Jackie Gates, who is on the way to making element 116. And so we are still in the business of discovering elements at Berkeley Lab and doing a number of, again, other really cool, exciting things from quantum sensing and materials to, again, thinking about the ways in which we can support the earth as it is in terms of energy conservation, renewables, and anything else that would support our daily lives. So I'm going to end by having us do an aerial tour of the 200 acres of Berkeley Lab. So you'll see that on the next video, and it's going to play now. So thanks, Julia. You can play it. right, and thank you all so much for hopefully what we call the best view from a lab, Berkeley Lab, and we'll pass it back to Julia and the team.
Thank you, Paige, for the wonderful presentation. And last but not least, now we're going to talk about, oh, I hope we can talk about it. Here you go. SLAC National Accelerator Laboratory, where I work. So SLAC National Lab is managed by the Stanford University and funded by the Department of Energy. It's located in Menlo Park, California, and it's a small lab. We're squeezed between the campus of Stanford, and it's only 426 acres. We have almost 2,000 employees coming from 55 countries, 300 postdocs, so not as big as Los Alamos that had tens of thousands, no, thousands of postdocs, but still a lot of opportunities and yeah, postdocs, graduate students, and obviously we all host a lot of internship during the summer. There were 4 Nobel Prizes awarded to 6 laureates for the research conducted at SLAC. Our mission is to explore the universe at its largest, the smallest case, through innovative scientific tools. So what are the SLAC is also a multidisciplinary lab. And so we study a lot of topics, and our scientific focus is really wide. We study X-ray ultra fast science, the physics of the universe. With advanced accelerator technologies, we have one of the most advanced linear accelerator, study the science of life, and that means that, yes, with our accelerator, we study very condensed matter, but also very soft biological system at the molecular level. And we help discover protein, viruses, cellular system. We help support inventing new technologies, create novel tools, instrumentation for science, and also advanced detectors for particle physics, data processing system, and nano fabrication system. And also we do energy science, clean, sustainable solution for the world's energy challenges. 3 of our big facilities, our big proud and joy of SLAC National Lab are the LSST camera that we built for the Rubin Observatory in Chile. The camera took a long time to build. It's now installed in the observatory and soon will start mapping the sky. And not only, and we thought the big challenge was to really build the camera, but now we need to analyze all the data that the camera is going to give us, and it's an enormous amount of data that our astrophysicists will collect, remove the noise, analyze, and make new discoveries about the galaxy and about all the everything outside our solar system. We have also a linear electron accelerator. We accelerate electron to produce X-ray. It's called linear coherent light source, and the X-ray that it produces are extremely high in frequency and in energy, well, the energy is a big spectrum of X-ray energy, so we can test from materials and batteries and condensed material to do biological studies. So really allows a lot of users to come to Slack to use this accelerator to do their studies, publish, and have a lot of impact on our daily life. And we also have the Stanford Synchrotron Radiation Light Source, SSRL. And this is a circular electron accelerator that produces X-rays. And here also we do study with X-rays, and a lot of users are coming and doing their tests in the facility. We also have a cryo electron microscope for testing biological protein, DNA materials, and a nanofabrication facility that is part of the huge collaboration about nanofabrication around the various national, between a few national labs. And I have also a video that shows an aerial view of the linear accelerator and really some of the main studies that happens at SLAC.
Welcome to SLAC National Accelerator Laboratory. Thousands of people from all over the world come together at SLAC to do science that helps us understand the world we live in and improves our everyday lives. SLAC is a Department of Energy national lab run by Stanford in the heart of Silicon Valley. We invent scientific tools to explore the universe at its biggest, its smallest, and its fastest. From the tiniest of particles to the expanse of the cosmos. From the molecular machines that are essential to life and finding cures for disease, to future technologies for computing and clean energy. Our bold and creative people are the heart of everything we do, combining their talents and expertise in a spirit of collaboration, integrity, and respect as we build a better future together.
Okay, and with this, we conclude our, see if I
Welcome
manage to stop
to
it. Okay.
SLAC National Accelerator Laboratory.
Will I be ever able to stop sharing this? I don't know. Here you go.
Yeah, that's it.
Here you go. And with this, do you have any questions? You have been pretty quiet today, so please type your question in the chat. We hope you're curious about coming visiting the National Laboratories this summer. Most of you will join us during the camp. Do we have any questions?
So Julia, someone was commenting about the picture that was shown with all the scientists and saying, you know, we hope that in the future scientists get together again. And my answer was, we are in fact working very closely to each other. So although I work at Los Alamos National Laboratory, I might go to another national laboratory to do experiments. And same goes with other national laboratories. So Livermore, Los Alamos, Sandia, we work on some national security topics and we do experiments together at the test site or other places. Or we will go to SLAC if we want to do certain measurements, and synchrotrons or accelerators or whatever. So in fact, we work very closely to each other in many of these very large projects.
Are there any bioengineering breakthrough currently going on in any of the labs? Bioengineering breakthroughs. Maybe we are waiting for you to actually come and make a breakthrough.
I can
GP?
attest to some of
Yes.
the work at Brookhaven.
Oh, terrific.
So I mentioned our biology department, and we have a whole slew of people, but it's not specifically, I guess, the nature of an interdisciplinary lab, and the beauty of it is that there are not just biologists or working in a silo, or chemists working in a silo, or physicists working in a silo. They kind of all work together, and a very common theme throughout the other national laboratories is having scientists come and use these extremely powerful, unique facilities. So I know Brookhaven works on biofuels, genetically modifying plants in order to overproduce oil to be used for fuel. And then also at the National Synchrotron Light Source, a lot of scientists from across the country and across the world will come and bring their samples of whatever. A lot of protein crystallography is done there. And then they have their own breakthroughs in collaboration with Brookhaven.
Thank you, Teresa. And you can see also there are a lot of links in the chat about bioengineering at different at Los Alamos, at Livermore,
Yeah, one thing we
bioengineering
had
program.
this brain on a chip where you actually try and take neurons and neural activities and put them in cell cultures and be able to simulate things outside of the body, or using nanoscale technologies to counter biothreats. So I put a couple links in the chat there if people are curious.
Thank you, GP. Very exciting. Any other question? What are you, after attending Sage Camp, can high schooler partner with scientists at the national labs to work on projects or internship during the school year? There's, if you have specific projects that you need help with, you can certainly reach out to the education department of the national lab that is close to you to receive some support from the national labs, that's for sure. We also have our SageX club that create the liaison between the national lab and the high school, and there's a lot of they develop project during their club time, and internship during the school year, I'm not sure, but certainly internship during the summer.
So here at Los Alamos, we have both high school and undergrad internships, and many students have year-long. That means that you work few hours. You don't work 40 hours a week if you're still in high school, right? Or you're an undergraduate. But yeah, students can go throughout the year. So when you come for your school break, you can go back to your group where you were doing something. I want to add something else. If you're a high schooler and are working in a science project and need some help, don't hesitate knocking at doors. Many of our scientists are mentors also in something called Supercomputing Challenge here in New Mexico. We are not formal mentors, we just help out. We are also the judges for those, so we need to make sure there's no conflict of interest and things like that. But my advice to you all is, if you are curious or interested, just contact people, talk to people, be insistent, don't give up. If you send one email and they don't answer, we are busy. So keep knocking until we point to point you in the right direction or to the right person. If you ask me something about bioengineering, I know very little about bioengineering, but I will try to figure out. I'm sure I know someone who can answer that question. So keep knocking at those doors. Find the names of those people on the websites. You can Google our websites and get the answer, get the answer that you're looking for.
Absolutely, lots and lots of scientists and engineers are happy to help and happy to answer your question. Will you assign a mentor scientist for each camper? I'm not sure there's any in any camp we really directly assign a mentor scientist. During the camp, you will have a chance to meet really and discuss and talk with a lot of scientists, probably 80 scientists is better than one, what I say, and you will have the chance to talk with all of them and probably contact the one that you feel is more interesting, has the more interesting topic, and you can relate to. So I think it would be limiting. If we assign only one person, it's going to be limiting your possibilities and opportunities. You'll have a chance to speak with many of them and listen to their stories, their research, and then create contacts with them. Thank you for your question, Frank.
But also, several of our students that got internships at Los Alamos, they found their mentor during the camp. So the ball is in your court. We expose you to many scientists, and it's up to the student then to go and talk to them, go and ask them if they have internships available, if they are looking for a student, and things like that. So you guys are empowered to do those connections after we try to coalesce, put all these people in front of you, right? It's on to you.
Any other question? What does the day look like for a typical camper attendee in terms of both in research and daily activity? Okay, you will receive a very full schedule of your summer camp for all of you, I'm sure, between speakers, talks, and hands-on project, and tours and visits and the reflections and leadership activities. You will receive a very active and very full schedule, and all the information are going to be sent to you before the camp. The day, yeah, it's gonna be you make sure you get good sleep during the night. If it's a overnight, well, anyway, for day camp, overnight camp, good night sleep, because you need a lot of energy during the day. We're gonna start early and fill your day with a lot of activities, a lot of interesting information. If you need the specific information on how the day looks like, please contact the coordinator of your camp directly. Do you have any other questions? Okay. If not, please, thank you for joining us. Please follow us on social media, Sage's Camp on Instagram and on YouTube for our Sage Live recording. And if you have, need any information, write at info@mysagejourney.org. Thank you for joining us. Stay in touch and see you soon.